So you're running comfy UI on an Nvidia DGX Spark, but you're just not getting that mind-blowing performance you were expecting. If that sounds familiar, you are in exactly the right place. Today we are going deep, and I mean deep, into the specific configurations you need to unlock the full petaflop of power sitting in that desktop supercomputer. Let's get right into it. And let's just start with a really direct question. You've got a DGX Spark. That's a petaflop of AI power right there on your desk. But here's the thing, a standard comfy UI install, it won't even get close to touching that power. In fact, it's pretty much guaranteed to fail entirely. We're going to fix that right now. And that brings us to the first and honestly biggest hurdle, the software stack. You see, the Blackwell architecture is so new that all of your standard installation methods, the ones that have always worked for you before, they're just not going to cut it. Let's break down exactly why.
Okay, so here's the absolute core of the problem. Your stable, off-the-shelf PyTorch releases literally do not know how to talk to Blackwell's new Tensor cores. It's like they're speaking a different language. They don't understand the FP4 data format, and they can't even begin to comprehend the unified memory architecture that makes the Spark so incredibly fast. It's kind of like trying to run a modern ray-traced game on a 10-year-old operating system. The foundational language just isn't there.
And look, this isn't just some abstract, theoretical problem. This is a real quote from a real user on the front lines battling what we all know as dependency hell. So if you felt this exact frustration, believe me, you are not alone. This is what happens when you're working on the absolute bleeding edge. It demands a very, very specific setup.
So here it is. This is your solution. And I need to be crystal clear here. This table is not a suggestion, it's a requirement. Every single component on this list must meet that minimum version. If even one is off, you're not going to be creating incredible content, you're going to be debugging Python errors all day long.
Let's just zero in on the most critical parts here. CUDA 12.8 or higher is absolutely non-negotiable. It has the new instruction sets that actually unlock FP4. You've got to use PyTorch nightly builds because the stable releases are just way too far behind. And please pay very close attention to your Python wheels. If you're running Python 3.12, that wheel file name must contain CP312. Oh, and a final pro tip, use a virtual environment. It will save you so much headache from blowing up a working install when you're just trying to test a new custom node.
Now, when it's time to actually install this stuff, you basically have two main choices. If you're someone who is constantly tinkering, always trying out obscure custom nodes, then the manual pip install gives you that flexibility. But, and this is a big but, for a stable, high-performance, ready-to-go production environment, the Nvidia Docker container is, without a doubt, the way to go. It's pre-configured, it's optimized for Blackwell, you just get right to work. All right, with the environment finally built correctly, it's time to get to the fun part, wiring up the workflow itself. We're going to start in the engine room with the two nodes that will give you the single biggest performance jump possible, TensorRT and NIM. So what is TensorRT, really? Well, it's way more than just another node in your graph. Think of it as a special compiler just for your AI models. It takes a generic model, like SDXL, and it completely rebuilds it from the ground up, optimizing every little piece to run as fast as humanly possible on your specific GPU, taking full advantage of those Blackwell tensor cores. And here's what that looks like inside your comfy UI graph. You just feed a standard model into the TensorRT node. It does a one-time compilation, which can take a minute, and then it spits out a special .engine file. Now think of this file like a custom-built race car engine, perfectly, exquisitely tuned for the exact hardware sitting inside your DGX Spark. So then the question is, which node should you use? It's actually really simple. Use the TensorRT node when you're working with your own models, your custom fine-tunes, your experimental stuff. Use the NIM node when you need production-level speed with officially supported models like Flex 1. The NIM node is amazing. It just pulls down a pre-optimized, pre-packaged microservice directly from Nvidia, giving you maximum performance right out of the box. Okay, now let's take that performance and kick it into an entirely different gear. If TensorRT is that custom-built engine, then Sage Attention is the bespoke turbocharger, designed specifically and only for the Blackwell architecture.
And the performance gains we're talking about here are just staggering. Seriously. We are looking at a 2.7 to 5 times speedup over the fastest flash attention implementations out there. This is not some small incremental improvement. This is a leap forward that will completely transform your workflow.
So how does it do it? What's the secret? It's all about FP4 precision. This tiny 4-bit data format is a key hardware feature of Blackwell's tensor cores.
By using these much smaller data types for the trillions of calculations involved, you can just do massively more of them at once, and that is the key to its unbelievable speed.
But what about quality, right? That's always the concern with lower precision. Well, this is where Sage Attention is incredibly smart. It uses this really clever two-step process to avoid losing any detail. First, per-token quantization looks at the values for each individual token and scales them to fit perfectly within that tiny 4-bit range. Then, microscaling applies a second scaling factor to that already normalized range to preserve all the fine details. The result? A massive speed-up with absolutely no perceptible loss in quality. It's brilliant.
So, we have a perfectly tuned, high-speed software environment. What can we actually do with all this power? This is where the DGX Spark's unique hardware truly starts to shine, letting us build workflows that are just fundamentally impossible on consumer-grade GPUs.
And it all really comes down to this one single game-changing number, 128 gigabytes of coherent, unified memory. Now, this isn't just a ton of VRAM, it's a massive, shared pool of memory that completely changes the logic of how you even think about building your comfy UI graphs.
What this means in practice is that VRAM limitations, they're basically a thing of the past. The whole dance of loading a model, running it, unloading it to make room for a control net, then unloading that to run an upscaler, that's over. You can now load everything you could possibly need for a complex shot, all at the same time. I mean, just imagine for a second what a real professional video workflow looks like when memory is no object. You have your main stable video diffusion model loaded, and right next to it, 3 different character LoRa's for shot consistency. Then add multiple control net models for precise posing and your face swapping and restoration nodes for post-processing, all of them active, in the same graph, ready to fire instantly. It's a whole new world.
Okay, finally, let's talk about the end of the line, the final output. Delivering flawless, professional 4K video takes a very specific technique. And guess what? The DGX Spark gives you a massive advantage here too.
And that technique is called tiled diffusion. The core idea is actually pretty simple. Instead of trying to generate a huge 4K image all at once, which is really inefficient, you break it down into smaller, overlapping tiles. You process each one individually, and then you just seamlessly stitch them back together into the final high-res frame. And this is where the Spark's 128 gigs of memory gives you a direct, tangible benefit. All of that memory lets you use much larger tile sizes, and you can process more of those big tiles in a single batch. What does that mean for you? A faster and, more importantly, a cleaner upscale. And this brings us to a really important quality insight. The bigger your tiles can be, the fewer seams you have to stitch together. This drastically reduces the chances of seeing those ugly, grid-like artifacts that can just ruin a tiled upscale on a memory-constrained system. It's a direct line connecting the Spark's hardware capacity to the final creative quality of your work.
So when you put it all together, the cutting-edge software stack, the compiled models, the hardware-specific attention, and that massive unified memory pool, what you get is truly transformative performance. Local generation gets so close to real-time 4K that it really makes you wonder, is the DGX Spark no longer just a rendering tool, but maybe something more? An active, creative partner in the process? Thanks for tuning in.